Today, I'm helping out Robert Moss as he prepares for his data science interview. These interviews can be pretty daunting and challenging. I'm hoping this video will be beneficial to both practicing data scientists who just want to revisit some of the fundamentals, as well as people who are trying to crack into the field and prepare for their first interview. I hope you enjoy our discussion, so let's jump into it. Say you're building a binary classifier for an unbalanced data set, where one class is much rarer than the other, say 1% and 99% respectively. How do you handle such a situation?
Yeah. So how I would handle this situation is first I'd see if I could get more data, like on the rare class, to see if I could add that to my data set. Failing that, I would choose an evaluation metric like precision, which is the proportion of actual positives that were predicted positive, or recall, which is also called the sensitivity, which is the percentage of total positive cases captured out of all positive cases, or the F1 score, which is the harmonic mean of precision and recall. Also, you'd want to look at ROC curves to evaluate the models as well. And then you could also try undersampling and oversampling. There's some out-of-the-box techniques from Imbalanced Learn. And you could also try generating synthetic examples of the rare class using SMOTE, which creates synthetic examples of the rare cases. You could design your own function, which penalizes the wrong classification of the rare classes more than the abundant classes. Or you could resample the classes by running ensemble methods with different ratios of the abundant class to the full set of the rare class.
That's a pretty complete answer. I think, so this is a common question, I think, how to handle an imbalanced data set. Yeah, that's good. Yeah, so the metric, first of all, the original metric can change, which you said that, you might not want to use accuracy as a metric for an imbalanced data set, which is perfect.
Mm-hmm.
I think that's good. I think, I've found from my personal experience, SMOTE has worked pretty well for these kind of problems when you have to do something like unbalanced data.
Yeah, like this question I took, I kind of got a lot of the points on my own, like using the metrics and stuff, but I also looked at the answer for like some of their other ones. So I'm a bit, I'm a bit fuzzy on using the ensemble methods with the different ratios of classes. I don't know why you just wouldn't undersample and just use like it's like kind of the same amount. Like use
both, right? If
huh?
you have enough time. If you have enough time, you can try both, right?
Yeah.
I think the ensemble, that's probably a bit more advanced. Probably don't need to worry about that quite yet.
Yeah. Okay, great.
One thing I was going to mention, you mentioned recall and precision. Do you know where that one come from? Like, do you know when it was originally studied, like, or the terms like recall and precision?
No.
I think it was for like it helped me understand better what it is. So it's for information retrieval.
Mm-hmm.
So suppose you do like a Google search or whatever.
Yeah.
So you get back like however many results, like a lot, right?
Yeah.
Precision is the amount of results that you get back that are actually like the proportion of results you get back that are actually relevant to your query.
Yes.
So precision is that one, and then recall is like the total, like the proportion of relevant results that you actually get back in your query.
Yeah. I mean, like how I know it is like precision is true positives over true positives plus false positives, right? So that's kind of like the precision of like, it's that's why it's like the proportion of like the positives that you get over like all the positives, right? And then with recall, that's your sensitivity, which is true positives over true positives plus false negatives. So that's like your, how many true positives are actually positive, right? So yeah, that's how I kind of tend to kind of memorize those ones.
I was just saying the example because for me it helped me remember it better because then I have like the concrete thing to think about.
Yeah. So you're saying that with Google searches, precision is the amount of like the search results that were actually relevant to your query.
So precision would be the proportion. It's always a proportion. The proportion of the proportion of results that you get back that are relevant to your query, exactly.
Yeah, cool.
And then recall is hard to measure in the Google search because like it's the proportion of results that are relevant that you actually return. But how do you measure how many results are relevant? That's like pretty tough.
Yeah, yeah, yeah. I didn't like the way the book kind of talked about precision. You know, how they say like on page 93, it's like precision is the actual positive proportion of observations that were predicted positive. A weird tongue twister.
Yeah, I mean,
There.
you can just memorize the formula if you want, I guess.
Yeah.
I mean, probably you don't really. Maybe you can impress someone by having the formula memorized, but it's not that important.
Yeah. I mean, I would just say that, you know, like if I were to say it's like precision is, I mean, it's like talking about this correctly and using the proper vocab is important for me with job interviews because you just want to, you know, you don't want to sound like you don't know what you're talking about. And so, you know, when you're saying precision, it's like the true positives over true positives plus false positives, but those are all predicted by your classifier, right? Like it's these are all predictions done, right? So like the false positives are also predictions done by your classifier as well. So what would be kind of like a proper sentence structure to kind of like talk about that, where if you say, if you were to define precision, you would just say precision is my ratio of true positives. Is my
Let me share my screen real quick.
yeah, it's like percentage of true positives over all positive cases is probably that I would say.
So of course you know the confusion matrix, right?
Yeah, that's what I'm looking at right now on page 93.
So then precision was which one? You're saying true positive over true positive plus
Yeah, dude, you want to get a different image. Go back to like the images and stuff.
a better image, you're saying?
Yeah. Go to the images.
Like this
And
one?
you want to get you want to get that one second row, second one in from the
this one.
that guy.
Is this a beast of a one? Yeah, okay.
There you go. Because now you got precision up there, right? Sorry, hold on. Yeah, you got. Oh no, this is a beast of a one. It's almost too complicated.
Actually, precision is right here. Okay, good. But yeah, it's like I think the way you should think about it is like, or the way I think about it is like, yeah, exactly. Like this row here is like the test positive.
Yeah.
So this is like the proportion of the ones that you guessed true of all the ones that were true in your test, like actually.
Yes. Yeah.
So yeah, I guess you could say it like that. The proportion of ones you predicted true that are, you know, of
all the true cases, the proportion of
cases.
what we predicted true to all of the positive cases, false and true, you know, true positives and false positives. Yeah.
So that's like this green, upper green box over the green plus the red.
Yeah.
And then the recall is, I guess you do.
Is the predicted like true positives over the actual positives. So it's true positives over true positives plus false negatives, which were actual positive cases, right? So it's like how many true positive cases you caught from the actual positive cases.
Is that right? Yeah, I guess so.
Yeah. Or is it?
Okay, so I said precision wrong. Okay, so precision is true positive over the total number that you guessed positive.
Yeah.
Okay.
Yeah.
Right. So precision is true positive over.
Find a different
so
image.
It's the amount you guess correctly, the amount you predict correctly over the total number of ones that you tried to guess. Positive.
Yeah. Yeah. Over the total positive predicted.
Huh?
Yeah. False. Yeah. False or negative. Yeah.
So I think it's pretty natural to struggle with wording this kind of thing.
Yeah. No, it is. And to get proper wording for it, I think is really good.
Okay. So So precision is the amount, like the amount that were positive that you guessed positive over the total amount that you guessed positive.
Yes. And then recall is the amount that you predicted positive over the total amount of true positive cases.
Cool. So, and then one other thing you mentioned is ROC curve, which maybe we'll talk about.
Yeah. I mean, from my understanding, it is a metric for which to evaluate classification models. It gives the amount of true positives to true to false positives over different thresholds of probability.
Yeah, exactly. Your model, when you train a classifier, typically the model outputs a probability, right?
Yeah.
So you could say, well, I could either say, you can pick which probability is going to be your threshold for whether you guess something's positive or negative. So typically out of the box, though, you'll guess 0.5. That'll be your threshold.
Yeah.
But as you increase your probability, or as you increase your threshold, that's going to change your model quite a bit.
Yeah.
Yeah, exactly.
Yeah. So on our bottom, like left corner, because it's true positives over false positives, when we're at a 0 threshold, everything is going to be a true positive.
So nothing's going to be, I think it's 0 for each of them, right?
Yeah. Yeah.
So you're always guessing negative for this bottom left.
Yeah.
And then on the top right, you're always guessing positive.
Yeah.
So the threshold for this one, yeah, it would be 1 and 0. Yeah, that's a good one to explain, like the top right and the bottom left, like why they're 0, 0 and 1, 1.
Yeah.
And that's, yeah, exactly, picking your threshold at those extremal cases.
Yeah, everything's because you're doing everything positive. So yeah, so there's going to be like 100% false positive rate.
Exactly.
Yeah. Yeah. And the better model has more area under the curve.
Yeah, I mean, that's up for debate a little bit, but I think that's a pretty standard way of doing it. I think it's quite clear if one model give you like you see the blue line is like completely above the green line in all cases.
Yeah.
Yeah, I think that's kind of the area under the curve is one metric. But really, if you really want a complete picture, you should look at every single point on the curve, right? But it is always nice to have a single number that kind of tell you which model is better versus the other. So that's why. Now, like maybe the area under the curve is better for one versus the other, but the other one, there's a particular value for a threshold that you actually prefer. So
okay,
you couldn't say, yeah, but I think what you said is fine. It is pretty much better.
Yeah.
What are some differences you would expect in a model that minimizes squared error versus a model that minimizes absolute error? In which cases would each error metric be appropriate? So first of all, before you answer that question, define what the absolute and squared error are.
Yeah. So the mean squared error is going to be the sum of the differences between the sum of the squared differences between your predicted value and the actual value for your target variable divided by the amount of instances.
Exactly. You can even say it quicker. You can say it's the average. It's the average of the residuals squared, or the average of the sum of the residuals squared.
Yes, I like that. Yeah, the average of the sum, because the residuals is the difference between. Yeah,
and then if they say, okay, what's a residual? Then you can say, well, it's the predicted minus the target. All right.
Yeah, yeah, dude. No, love it, man. Love it. The absolute difference of the residuals divided by the mean of the absolute difference of the residuals, where the mean squared error is the mean value of the residual squared.
The mean, well, no, that was the mean squared. So the mean squared, that's that one.
Yeah, yeah.
And then what was the other one? The mean absolute error is the mean of the absolute value of the
residuals.
Like the mean of the sum of the absolute value. The average value of the absolute value of the residual.
Yeah, the average of the absolute value of the residual.
But it sounds like you know the formula in your head, so you'll be able to.
Yeah,
matter of trying to communicate it quickly as possible.
No, but again, saying it is, there's one thing to know the formula and write it on a whiteboard, but it's another thing to say it and to say it properly, because as a data scientist, you need to kind of talk about these concepts to non-data science people, I imagine, on the job, or kind of it's what they tell me.
Probably don't have to mention residuals too much to them, but maybe.
Yeah. So with this question, I mean, with me, the only really thing that I can come up with is that the mean squared error gives a higher weight to larger errors because it's squaring the residual. So it's more affected by outliers than the mean absolute error. So if you have a data set that has a lot of outliers, you would want to use the mean absolute error in that case.
Yeah,
that's about the only, and that's the only kind of thing that I can see. I do know that the book talks about more, so maybe we can kind of look at their answer, try to tease out some more of what they're saying.
Yeah, there's one thing that, yes, that's right. If you think your data has a lot of outliers, it maybe makes sense to try the absolute error. Of course, you can try both, right, and practice and whatever, test it on your metric. But anyways, so here's the real difference. So if you minimize the mean squared error, you're kind of trying to find the mean of the data. Whereas if you minimize the absolute error, you're kind of trying to find the median of the data.
Yeah, they mentioned that. Why is that?
They kind of mention it. They say proof of so the optimality property.
Mm-hmm.
So when you just see the absolute value, eventually they just find the median.
Okay. And the median, again, is more robust to outliers because it's the actual like halfway point in the data in our distribution.
Basically, we're going to have a bunch of numbers, say x1, x2, and so on and so forth.
Mm-hmm.
This is literally has nothing to do with machine learning. This is just math.
Yeah.
So let's think of these like numbers as fixed.
Yep.
And then you can construct like, so from here you can have either the first one or the second one, not squared. So just the second one like this. So the first one's basically without the mean. It's the square error, and the second one is the absolute error.
Yeah.
So you can ask, when the xi's are fixed, what's the value of mu that minimizes this equation? Mu and m that minimize the above equations. And this is the mathy part. Like, it turns out that if you do some work, actually mu is the mean.
Yeah.
Of the xi's, and m is the median. So again, this has nothing to do with machine learning. This is just for numbers.
Yeah.
So I want to try to minimize the squared error versus the absolute error. One is the correct number is mu, and the other one is the median, like
Okay.
So if you put this back into your machine learning thing, eventually what you'll find is instead of trying to predict like on average what happens with your model, you're trying to predict, like if you use the mean squared error, you're trying to predict, if you use the absolute error, what happens like in the median, basically.
Yeah. So let's look at the solution on page 119 to this question and kind of read it together, right?
Okay.
We can denote squared error as mean squared error and absolute error as mean absolute error. Both are measures of distances between vectors and express average model prediction in units of the target variable. Both can range from 0 to infinity. The lower score, the better the model. The main difference is that errors are squared before being averaged in mean squared error, meaning there is a relatively high weight given to large errors.
Which is exactly what you were saying, right?
Yeah. Therefore, mean squared error is useful when large errors in the model are trying to be avoided.
So suppose you're trying to predict like salary or something, like,
yeah,
you might have like one person who makes like, a lot of money, but you really care about what happens to like the like people on average.
Yeah.
So you might want to use like a more of a thing that's more robust to outliers. This can happen, yeah.
No, but I mean, I don't get that sentence because it's saying that it gives a high weight to large errors, and it says therefore mean squared error is useful when large errors in the model are trying to be avoided. Okay, yeah. So basically, if there's large outliers, we don't want to use mean squared error.
I think more importantly is just getting, exactly. So the mean absolute error would be more robust to outliers.
Yeah, that's what I think the best answer to that question is. They kind of give it in some weird roundabout way.
Yeah, I think if you just say like, hey, mean absolute error is more robust to outliers, and then if someone want to grill you more on it, like you can try to remember the mean and the median and all that, but I don't think it's like crucial.
Yeah, well, I mean, I think it's pretty easy to explain. It's just like, look, you're squaring the residuals, so any large residual is just going to have a massive effect.
Yeah, but that shows you have some understanding of the loss function and what machine learning is trying to accomplish, which is good.
Yeah. And then it says here, mean squared error is minimized by the conditional mean, whereas mean absolute error is minimized by the conditional median.
Yeah, which is kind of what I was trying to explain before.
Yeah. That was the last sentence there.
And that's just some math. You don't really, you can derive that using calculus, but there's no need for us to do that.
Yeah. No. I mean, but I do want to, again, when we go through the individual, machine learning algorithms, like logistic regression, linear regression, I want to write out the mathematical formulas I need to know for like each one. And I'd like to write them using like matrix math as well as like, instance math. I don't know if I'm saying instance math right, but like there's different forms of equation, whether you're using like a matrix or like an instance. Because I want to get used to seeing them both differently, because it comes up when we look at like the beta coefficient and like that type of stuff when we kind of go further into these.
I think if we program it in NumPy, that should be good, right?
Yeah. Oh yeah. No. Again, like the way that you were doing it was just amazing.
We don't need to see the math formulas, but seeing how to program it in NumPy, I think is pretty insightful.
Yeah.
And then the math formula kind of you have to know it to
Yeah. No. And again, just like, I'll find the three equations, and then just to have you explain the difference between like, when kind of certain stuff comes in would just be great, because you got the PhD in math. So, yeah.
I think, they mentioned some other things in here that mean squared error have to do with maximum likelihood estimation of a Gaussian. Again, maybe we'll talk about this in the future, but probably something we don't need to grill on right now.
Yeah. Again, like I think all these like little side notes they have, we'll go through when we're doing, the other, like the other things. And again, I think those videos would be great for like learners to actually like go through, because nobody really does that. Nobody looks at like actually how it looks. Like I never seen anybody do that, with like NumPy.
Oh, one good thing to think about in terms of median and mean.
Yeah.
Actually, probably the easiest one is like the lottery. The mean is going to be like losing. Everyone's going to lose basically.
Yeah.
But for like one person who like wins a lot, and that kind of really changed the mean, if you want to remember the difference between median and mean.
Yeah, no, I like that. That's a really good example, especially with like outliers. Let's go on to 7.3, Facebook. When performing k-means clustering, how do you choose k? Basically, you create a chart that shows the percentage error of your classifier on the y-axis. So it's going to be the amount of clusters k. Well, k isn't the measure of clusters, but k is the amount of neighbors that defines a cluster.
Do you remember which one k-means clustering is?
Yes.
What's that? Yeah, just remind me of the algorithm.
Okay, so the algorithm, it's hard to explain, but
what's the result of the algorithm? What do you get?
A classification.
A classification, but you get like, all right, you get like k vectors, right? Or I think you're thinking of k nearest neighbors. That's why I'm asking.
Yeah, I am thinking of k nearest neighbors.
But this is k-means clustering, which is slightly different.
Okay. Yeah.
K is actually a number of clusters that you are, gonna.
Oh yes, clusters. Yeah.
And then you plug it into this algorithm, and it produced basically a divide your data set, or well, it provided an algorithm for determining which one of these k clusters, a data point will lie in.
Mm-hmm.
Right. So that would be like, that's roughly what k-means clustering achieves.
Yeah. And so is it so it's an unsupervised method then?
Exactly. Yeah, it's a clustering algorithm. It's just you don't need labels.
Yeah.
Which you can imagine might be useful in practice.
Yeah.
Then the question is, okay, so how do you choose k? First of all, you'll run the algorithm for different values of k.
Mm-hmm.
And then you have to figure out, you should definitely plot like k as the x-axis, and you should plot two graphs on the y-axis. One being like the training, either accuracy or whatever metric you're going to use, as well as the validation.
Yeah. But because it's unsupervised, how are you like measuring the accuracy? So
because to train the algorithm, you'll need some sort of loss function, right?
Yeah. Okay. But yeah, I'm looking at their answer.
And they mentioned the elbow method, which is
yeah.
Actually, now I'm thinking about it, for k-means clustering, you might not even have a validation set. Yeah, exactly, because you might not even have a validation set.
Yeah. So it says the elbow method is the most well-known method for choosing k and k-means clustering, but that's also going to be for k-means classification as well. So it says the intuition behind that technique is the first few clusters will explain a lot of the variation in the data, but past a certain point, the amount of information added is diminishing. Looking at a graph of explained variation on the y-axis versus the number of clusters k, there should be a sharp change in the y-axis at some level for k. For example, in the graph that follows, we see a drop-off at approximately k equals 6.
Hmm.
Note that the explained variation is quantified by within cluster sum of squared errors. To calculate this error metric, we look at for each cluster the total sum of squared errors using Euclidean distance.
Okay, I can explain roughly so that you'll.
Yeah. Another point I'll do is determine. They say the silhouette method, which aims to measure how similar points are in the cluster compared to other clusters.
So this is the graph, right? Like something like this for the.
Yeah.
So the x-axis, like, yeah. So I had said something a bit wrong before, because in this one, maybe you won't even have a validation set. Maybe you're just trying to figure out what k you should use on your train set,
Mm-hmm.
which is always a little sketchy. But anyway, so if that's what we're doing, k is still the x-axis, and y, this is, they say, the sum of squared distances.
Yeah.
And you'll notice that it's strictly going down. So the larger k is, it turns out, for k-means clustering, you should get a smaller value for the loss function.
Mm-hmm.
So that's one thing to note. And then the natural thing to wonder is if we're getting better results, are we kind of overfit into the training set? That's the natural question that should come.
Yeah.
And the elbow method is kind of like saying, like, okay, as soon as this kind of like flattens out, that's probably roughly when we're going to start overfitting. That's kind of the hope, or the hypothesis.
Yeah.
Then the question is, what is the sum of squares distance?
Mm-hmm.
So you can kind of see there's three kind of clusters.
Yeah.
Blue, green, and yellow, and you can see those big black dots. So the dot is kind of what's determined, like, if under
The center
hood,
of the cluster.
yeah, roughly.
Mm-hmm.
So what you do, how you determine if something is in what, like, which, like, how do you determine if a point is green, blue, or yellow? What you actually do is, for a new point, you compute the distance to each one of these black points.
Yeah.
And whichever one gives you the smallest distance, that's the color of the new data point.
Yeah.
Right between the green and the blue, those points are roughly the same distance from the black point in the blue versus the black point in the green.
Yeah.
So to determine what cluster, and you're computing the distance of this new point to each of these black points, and then taking the smallest. So then the sum of the squared distances would be like the total sum over all the possible points of all of the squared distances. So, like,
and that's why it goes down as we add more k's, because we're getting less and less distance because we have more of those fellows. Yeah.
Yeah, so like this point, this green point that's really close to this black point, it's basically going to contribute next to nil because it's so close.
Yeah.
In that total sum, but you're going to sum over everything. So like some of these far ones are actually going to be like a big contribution.
Mm-hmm.
But anyways, that's how it is. So the sum of the squared distances would be, you sum over all the possible points, and you take the sum of the squares.
Yeah.
Yeah, so that's what the error is. And as you said, like, for instance, if I had 4 points, I could just take these 3 points, and I could take another point, and it's going to make it smaller, like any other point, really.
Yeah.
Because it's only going to make the sum of the squared distances smaller because of the additional point.
Yeah.
So this is why it tends to go down. So anyways, this is k-means cluster, and it's a and one way you can determine which one you use is, or which value of k you can choose is.
Yeah, so it says in, another popular alternative to determine k is k-means clustering is to apply the silhouette method, which aims to measure how similar points are in the cluster compared to other clusters,
Mm-hmm.
where x is the mean distance of the example's nearest cluster. A value of 1 implies that the point is in the right cluster, and vice versa for a score of -1. By plotting the score on the y-axis versus the k, we can get an idea of the optimal number of clusters based on this metric. Note that the metric using the silhouette method is more computationally intensive to calculate for all points versus the elbow method.
Fair enough. But anyways, I think, right, yeah, maybe the y-axis is harder to compute for the silhouette.
Yeah.
That is a common error, is to, I think, confuse k-means versus k nearest neighbor.
Yes.
So that would be a good one to not confuse.
Yes.
So k-means is unsupervised, and k nearest neighbor is typically, or is supervised.
Yeah. So 7.4, how can you make your models more robust to outliers? All right. So I'm going to say, because it's using like models, like we're talking about all models here, I would say that you can use loss functions that are you can try to minimize loss functions that are more robust to outliers would be a first one.
That's what we just talked about for extensively.
Yeah. Yes. Yeah. We could also find metrics to remove outliers like the Cook's distance.
The Cook's distance, what's that?
The Cook's distance is a measure of distance between data points. Past a certain distance, you can kind of label thing as an outlier and not use it in your model in your model scheme.
So in general, just finding a method for removing outliers.
Yeah. Cook's distance is the estimate of the influence of any given data point. Cook's distance takes into account the residual and leverage, how far away an X value differs from that of other observations for every point. In practice, it can be useful to remove points with a Cook's distance value above a certain threshold.
Mm-hmm. So you mentioned outliers, like handling outliers, like maybe removing them. You also mentioned trying a different loss function. Any other?
Yeah. So looking at at their answers, they said add regularization to reduce variance. So we could do L1 or L2 regularization, which we need to go into more kind of later on.
So that's something to review. And yeah, I think connecting that to why it might help with outliers is a couple steps.
Yeah. And then try different models. So it says you can use a model that's more robust to outliers. For example, tree-based models are generally less affected by outliers than linear models, which makes sense.
What does that make sense?
Because tree-based models are more because they ask like a series of yes or no questions, which try to lower like the entropy and the information gain. And they also kind of, when you talk about like random forest and like gradient boosting trees, they use many models combined into one. So you're kind of taking the average over many predictions. So in my mind, those are going to be less affected by outliers in your data set.
But yeah, that's exactly right. Like it's kind of predicting yes or no. So you could hope that maybe an outlier would just kind of get grouped with other points.
Because again, if one of your trees is on like makes a decision on the outlier, necessarily your other tree is not going to have that because the outlier might not even be in that next data set that the next tree trains on, right?
Yeah, maybe it is, maybe it isn't, right? Yeah. So I guess like
I'm actually surprised they don't give more of an explanation on that, but they do say they just are generally less affected by outliers. And then it says you can Winsorize data, which is cap the data at various arbitrary thresholds. For example, at a 90% Windsorization, we can take the top and bottom 5% of the values and set them to the 95th and 5th percentile of the values respectively.
So this is what I had in mind when I was thinking of removing outliers.
Yeah.
You can kind of look at the data and say like which ones are.
Yeah.
If you ever look at a real data set, you'll find a lot of outliers and like different features and stuff. So you can kind of look and see.
Yeah. So you just remove the top 5 and the bottom 5% from your data.
Yeah. Pick a threshold, whatever. You can even pick different thresholds and try.
Yeah. And then transform your data. You can use do a log transformation when the response variable follows an exponential distribution or is right skewed.
Right. So this is kind of saying like the whole distribution is skewed. Outliers you don't necessarily think of as that.
Yeah, I wouldn't really think that either. I don't really like that answer to this question.
But frankly, if the data is right skewed, it's not normally distributed, but there's more points to the right as like, and they go out further, then you can sometimes use log to. It actually does work in practice.
Yeah, I mean, I know that does work in practice to transform the data to log, but that's more just to get better predictions. I wouldn't really say that's because of outliers. But
if you go back and think about why the log is doing better, have to do with how the data is distributed. There is some argument to be made in that what they're saying.
Yeah.
Yeah, the log make better predictions. The reason why it makes better predictions is because it transforms the data into something more, more amenable to machine learning techniques.
Yes, yes, yeah. And then, this one we got, which was change your error metric to more robust. For example, for mean squared error, change to mean absolute error or Huber's loss. And then it says remove outliers. Only do this if you're certain that the outliers are true anomalies, not worth incorporating to the model. This should be a last consideration since dropping data means losing information on the variability of the data. So when they're talking about Winsorizing data.
Yeah, so I guess Windsorize kind of mean like, I don't know if we said drop, but it kind of mean like you cap it. So if like
Yes, yeah. So
if you're doing
let's
like a housing data set, you might cap the number of bedrooms to be like 8 or something.
Yeah.
That kind of thing.
Oh, okay. Yeah. So yeah. So when you look at that, they also cap the price like above a certain like value or price. There's no longer.
Yeah, exactly. I think even there is a scikit-learn data set like the California housing. I'm pretty sure
We did that for an example because you said you could use two different models, one to predict if it's going to be like at the high price, and then another model to predict actually variation in the beginning price.
Yeah. But yeah, right. That data came to us capped, I think. So yeah.
Yeah.
Came to us Windsorized, I guess.
Yeah. So if 9% Winsorized, we can take the top 5 and set them to the 90. Yes. Yeah. So you take the top 5 and then you set them to the 95th and the 5th percentile of the values.